Here we are going to study hydrostatic pressure and its variation. We have considered here, you see in the figure, one container partially filled with the liquid. Suppose the area of this container is A. That is what exactly we have considered here. Cross-sectional area of the container A. Now, A into H is the column of this particular area that we have considered. Its volume becomes A into H. Then you want to find the pressure at the bottom of this area that we have chosen. Pressure at the bottom is going to be that at above surface, that is atmospheric pressure, plus mg upon A. This is the pressure because of the weight. So, it could be written as P0 plus mg upon A, and for this m we could write V rho g upon A. You see, V upon A is going to be H. So, this finally becomes P0 plus H rho g. This is the pressure at the bottom. You might say this is the absolute pressure. P0 is the atmospheric pressure, and these terms you are already aware. H is the height of the column, rho the density of the liquid, and g acceleration due to gravity. Here you see the equation in the form of y equal to mx plus c. If you want to plot the graph between pressure and this H, it's going to be a linear graph this way. But here we are considering the absolute pressure and the height of the liquid column. Suppose you are interested only in hydrostatic pressure, then in that case, since hydrostatic pressure is only H rho g here, this is hydrostatic pressure. If you want to plot the graph of hydrostatic pressure with this H, it's going to be a linear graph through the origin. Here P0 atmospheric pressure, H is the height of the column. Now, depending on the density of the material that is allowed to be immersed or that is thrown in liquid, there are three conditions that we will study in detail. But whenever, according to Archimedes' principle, whenever a body is immersed in a liquid, there is upthrust, and the upthrust is upthrust. Thrust means a pressure. Upward acting pressure, that is known as upthrust. Upthrust is equal to weight of displaced fluid. When the body is immersed in the fluid, when I say fluid, I mean liquid and gases both. Means this is applicable to both. When the body is immersed inside the fluid, the weight of displaced fluid, I said, I'll repeat, weight of displaced fluid, this is equal to the upthrust, weight of displaced fluid. Now, whenever you want to find the upthrust, you have to find out the weight of displaced fluid. Suppose the body is completely immersed, then you will take the total volume. If one particular volume is immersed, then you will take Vm into density of the liquid. Here, because you are saying weight of displaced fluid, you will take the density of fluid only. This becomes the upthrust. You might say upthrust. This is which acts upward, and the weight of the body already is going to be total volume, density of the body, that is solid immersed. Not only solid, even liquid is also immersed in gases. So, weight of the body immersed. This is the weight of the body immersed, and this is upthrust. Now, the fight of these two will continue whenever you allow something to drop in the liquid. suppose the weight of the body becomes greater. How could it be possible? When the density of the body immersed is greater than the density of liquid, in that case the body will sink, as I have shown in the figure number 1. This is the example when the density of the body immersed is greater. And suppose the density of the body immersed is less than that of the fluid, this one. In that case, the body is never going to sink. This will be partially immersed. In this case, we use both the term. You could say the body is partially immersed. You could also say the body is partially floating. But when both are equal, this is most fascinating situation when the density of both become equal, that is body immersed and that of the liquid. In this case, you see the upper surface of the body immersed, this one as I have shown over here, upper surface of the body immersed and liquid surface both will coincide. That means you might say this is upper surface of the liquid, you could say this is the top of the body immersed. Both will tally, both will coincide, both will appear along the same line. This is most interesting case of flotation, but this is possible only when both densities are equal. Here, a simple jerk is also not needed for the body to sink. Here, if you just push it, again it will come upward. But in this case, if you just push it, it will go down to certain distance.